Now we have three very interesting equations on the board. Equation number 1, equation number 2, and equation number 3. Now what does each one of them stand for? Well, the first one here is a mathematical statement of Michael Faraday's law of electromagnetic induction. I'll explain that in a minute. But basically, what it is saying is that the induced EMF or electromotive force in a conductor is equal to minus the rate of change of magnetic flux with respect to time, or E is equal to minus d dt of phi, where phi is the magnetic flux. The second equation here is just one of James Clerk Maxwell's equations. There are 4 of them, as you know. The third equation is a statement of Stokes' theorem, which I will explain a little later on. But for now, let's stay with Michael Faraday's law of electromagnetic induction for a minute. Now let's imagine a conductor shaped in the form of a loop, as you can see here. Now, if I was to take a magnet, arranged as you can see south north like that, and move it up and down above this loop, the magnetic flux due to this magnet would be cutting the surface area that is bounded by this conductor, by this loop. And as I continue to move this up and down, the flux will be changing. The flux that passes through this area will be changing all the time. Now, according to Michael Faraday, whenever there is a change of flux, an EMF is induced. In this case, an EMF will be induced, which will push current in the direction as shown here. Now, the magnitude of that EMF is what is given by this equation here. E is equal to minus d dt of phi, magnetic flux. But what is phi? What is magnetic flux? Well, magnetic flux phi is equal to the surface integral of B ds, where B is the magnetic flux density. Now, Michael Faraday's law says E is equal to minus d dt of phi. So here we can write E is equal to minus d dt of this one here, which is B ds. So let's circle it nicely there. So our E is minus d dt of the surface integral of B ds. But there's a current that's flowing or circulating around this circuit here. And in order to maintain this current, an electric field intensity is required. An electric field intensity E is required. So therefore, we can express our EMF in terms of the electric field intensity. So we know that the closed line integral of E dl is equal to the induced EMF. So this is equal also to E. Now up here we found E is d dt of the surface integral of B ds. So we can equate this and that. So here, this is equal to that. So we can write a new equation, the closed line integral, of E dl would be equal to minus d dt of B ds. Here is our new equation again. Now, before we go any further, we notice that the conductor here is not moving, it's stationary. What is changing is B, the magnetic flux density. So our differentiation should be in respect of B. So here we can write this as minus partial B, partial T ds. And of course, it's equal to the closed line integral of E dl. Another nice equation there. Now, here is a line integral. Over here, it's a surface integral. We can come over here and use Stokes' theorem to change this to that. Because the Stokes' theorem says the normal component of the surface integral of the normal component of the curl of the vector field is equal to the closed line integral of the same vector field around the line which binds the area, which is, you'll see here. So we can change this to that. Therefore, now we can write the surface integral of curl of E ds is equal to our surface integral of partial b partial t ds. Now, over here it's a surface integral, and here it's a surface integral. And the surface over which we are integrating on the right hand side is the same surface we are integrating over on the left hand side. Therefore, these two integrands must be the same. So we can write curl E is equal to, this is the minus sign, sorry, minus partial B partial T. And this is James Clerk Maxwell's equation. If you enjoyed the video, please comment, like, and subscribe. Till next time, bye-bye.